Okay, this video, and I think this is the last video of content for Chapter 3, we're going to cover covariance and correlation. Covariance and correlation. So the goal here is we're actually trying to relate two different data sets with one another and see how do they move with respect to one another. So the example we're going to work with is actually our original example. If you recall, the number of bedrooms in the homes in Latrobe, Pennsylvania. So this is what we were working with before, this X value, and we remember we had 6 homes, 3 with 1 bedroom, and then 1 with 2 bedrooms, 3 bedrooms, and 4 bedrooms. And what we're going to do is compare that with Y, the price of the home. So we're going to see what's the correlation between the number of bedrooms and the price of the home. So that's our goal here. We're relating two different data sets. So in this case, we're relating X and Y. So let's just deal with some definitions first. So covariance. So it's just the distance, or rather, it's a measure of how X and Y vary with one another. You can think of covariance, it's the measure of strength of the linear relationship between X and Y. So this formula is actually similar to the variance formula. We're taking every data value of X, subtracting it from its mean. We're taking every data value from Y, we're subtracting its mean, and then we're multiplying those two values together, summing them up and dividing by n minus 1. So very similar to variance. But we don't need to be too worried about this formula. We're not going to have to work with it by hand, but I just wanted to introduce it. What's more interesting to us is actually a measure of correlation, which we'll call core between x, y, or just this is r, and it's defined as the covariance divided by the standard deviation of x and the standard deviation of y. So we're multiplying the standard deviation of x times the standard deviation of y in that denominator. So what correlation is doing, it's measuring the relative strength of the linear relationship between the two variables x and y. And this is much more useful to us. So let's just look at some notes here. So correlation, it only can take on values between -1 and +1. So a correlation of 0, looking at this second note, a correlation of 0 implies no linear relationship between x and y. So what that means is regardless of whether x is increasing or decreasing, that doesn't seem to be correlating with how y moves, whether that's increasing or decreasing. By contrast, looking at note 3, a correlation close to +1 implies a strong positive linear relationship. So what does that actually mean? We're saying that as x increases, y increases. Or as x decreases, y also decreases. So we can think of it as moving in the same direction. So that's a positive linear relationship. That's a correlation greater than 0, and the closer it is to 1, the stronger the relationship. Whereas a correlation close to -1 implies a strong negative linear relationship. So this is just the opposite of a positive linear relationship. So as x increases, y decreases. As x decreases, y increases. In other words, they're moving in opposite directions. So again, any correlation value between 0 and -1 would be a negative linear relationship. And the closer it is to -1, the stronger the relationships. So correlations closer to -1 and 1, the relationship between x and y is strong, and correlation values close to 0 is indicating weak relationships between x and y. And this is saying that you see kind of everywhere, and it's that correlation does not imply causation. And this is certainly true. Things generally will move in tandem with one another, but that doesn't mean that one is causing the other. In fact, there could be a third thing causing the movement between x and y. So let's visualize what we're talking about here. So we've got three plots here. So here on the left, so this first plot, we're seeing a perfect negative linear relationship. So as x decreases, y is decreasing as well. Or I'm sorry, I misspoke. So as x is increasing here along the x-axis, so as x is increasing, y is decreasing. So we're getting this negative line. So this is a perfect negative linear relationship. Whereas in the middle, we're seeing no relationship. So the correlation is 0. Regardless of whether x is, say, increasing or decreasing, there's no relationship to whether y is increasing or decreasing. And then finally, the positive relationship. So as x increases, y is increasing at the same time. And so we're seeing this perfect positive linear relationship. So these are the extreme cases. This is correlations of -1, 0, and 1. This isn't how data typically are related with one another. It's generally not this perfect relationship or like a literally 0 relationship between the two. So let's look at some other examples, and I grabbed this from the textbook. And some of this is hard to read, so I rewrote the correlation values in each of the plots. So here on the top left, we have a correlation of -0.9. So we would say this is a strong negative linear relationship. That makes sense. That's similar to our plot up here on the left, right? As x is increasing, y is decreasing. And so that is a linear or a negative relationship. And we're sort of seeing the same thing in this plot as well. We're seeing as x increases, y is decreasing. But the relationship isn't quite as strong, which is why our correlation decreased to -0.6. So we might say that this is a moderate negative linear relationship. And then moving on here, we have a weak negative relationship, -0.3. So still, it's kind of hard to see. So these next two plots, this one and this one. So in this case, we're sort of seeing as x increases, y decreases still. And over here, as x increases, y increases. But the relationships aren't very strong, which is why we get correlations of only -0.3 and 0.3. So we might say that this is a weak negative linear relationship. And over here, we have a positive, or I should be consistent, weak positive linear relationship. And then our final two plots, so these are more, so that here we have a moderate positive linear relationship. So we have a negative or a positive 0.6, right? As x is increasing, y is increasing as well. So we get a positive value. And then even more extreme, we're seeing as x increases, y increases. And we get a correlation value of positive 0.9, which is close to 1. So we would call this a strong positive linear relationship. And notice how with these stronger correlations, the data are more clustered here, as opposed to over here, it's a bigger circle. And even up here, again, it's the data is rather clustered in one place, but as our correlation gets closer to 0, it starts becoming a little more scattered, that the circle just kind of becomes bigger and bigger in terms of what that cluster is looking like. So that cluster becomes closer together as we get that stronger relationship in terms of correlations. Okay, now let's just do one quick example. So we already introduced this. This was the Latrobe home. So X is the number of bedrooms, Y is the price of the home. So we've got our X values over here, our X and our Y values. And I went ahead and calculated the covariance in Excel. Like I said, we're not going to do this by hand. This will just be an Excel exercise. So I calculated the covariance. If you go back to, I think it was our second video for chapter 3, we found the standard deviation of X to be 1.26. So you can go back to verify that. And then I calculated the standard deviation of Y, and it's 92,000. Okay, and we ultimately want to calculate the correlation between X and Y. So we know that the correlation between X and Y is equal to R. R is our measure. And then it's equal to the covariance between X and Y divided by the standard deviation of X and the standard deviation of Y. So we just plug in. So our correlation was 101,000. Standard deviation of X is 1.26 multiplied by 92,000, 394.1. And when we do, we get a value of 0.86. So we would say there is a strong positive linear relationship between the number of bedrooms in the homes and the price of the homes. And this is in Latrobe, Pennsylvania. And we can just do a quick reality check. Does that make sense? And yeah, it does. As we increase the number of bedrooms, generally the value of a property will increase. So it makes sense that we are seeing a strong positive linear relationship between the number of bedrooms and the price of the homes.